So, now we are going to talk about the conditions of spontaneity of a particular process. So, different conditions for spontaneity. So, we want to just emphasize that entropy is not alone is the criteria. I will just remind you still is that it is still the criteria when you talk about an isolated system or talk about the system plus surrounding, but eventually we will see that is giving you different criteria when you look at only the system. So, again we start from the derivations that dq plus dw is nothing but dq reversible plus dw reversible, because both of them are equal to du. So, therefore, so then in that case we know that dw reversible. So, work done on the system. So, whenever we talk about only dw, remember we emphasize that it is work done on the system, not by the system. Minus dw will be work done by the system. So, work done on the system is minimal. So, therefore, it has to be less than dw or less than equal to. So, equal to sign denotes that when work done is done in a reversible manner, then of course, they are equal, otherwise they are unequal. Now, if you look at this particular equation, if this guy is less than this guy, then this has to be more than that. So, therefore, we can write that dq reversible is greater or equal to dq, and when you divide by the temperature, we can write that because reversible is just one path. So, dq does not have that cut thing. dq reversible by t is greater or equal to dq by t, and dq reversible by t we know to be ds, which is greater than dq by t. So, therefore, t ds is greater or equal to dq, or t ds minus dq greater or equal to 0, and we know that du is dq plus dw. So, therefore, dq is du minus dw, and dw is minus pdv. So, therefore, it is plus pdv. So, dt ds minus du. So, from this equation from 6 we get, and we substitute dq value from 6 actually. So, minus du minus pdv greater or equal to 0. So, you see that. So, that is what we get as the condition for spontaneity, because you see that wherever this condition holds equal to 0, then this is the condition for equilibrium, whereas if it is greater than, then it is the condition for spontaneity. Okay. So, now coming back. So, now you see that the reason that this greater or equal to 0 is, so here we know that this condition, whenever it is whenever this quantity is greater than 0, that denotes an irreversible process, because we talked about that, right. We talked about equality sign being reversible and inequality sign being the irreversible, and we know for irreversible process the overall ds total is always greater than 0. So, therefore, if this is the condition for spontaneity, then this is also the conditions for spontaneity when it is greater than 0. If it is equal to 0, then we are talking about an equilibrium process. So, therefore, the equality sign will hold for the equilibrium process. So, therefore, for inequality we will go for a spontaneous process, and equality will go for an equilibrium process by using this particular argument that ds dot greater than 0 for an irreversible process. We will show later a similar one directly from the entropy itself. So, now that we have here, what are the things that we can observe? We can see that immediately that if u du equal to 0, that means there is no change, and dv equal to 0, then from this equation. So, let us say that, let us call that equation number 7. So, from 7 we immediately get that T ds at a constant u and v, it is greater equal to 0, or ds for constant u and v, it greater equal to 0. So, for condition for spontaneity is wherever there is a change at a constant u and v greater than 0, then the process is spontaneous. Whenever it is equal to 0, the process is in equilibrium. Remember, here we are talking about the changes for the system. Now, again from 7, we can use the particular expression in 7 as TdS minus du minus PdV greater or equal to 0. Now, taking all the terms to the other side, we can get du plus PdV minus TdS less equal to 0, and now we can take V and S as constant, and we can write du for constant V and S is less equal to 0. So, therefore, now the conditions for spontaneity is that whenever du for a constant entropy and volume, if it is less than 0, then the process will be spontaneous. So, the above expression, for example, this one ds u and v greater than 0 for a constant u and v. So, if v is constant, then there is no work done, and if u also is constant, then there is no change in the internal energy. So, even if the entropy changes, then the then you can say that ds u v denotes the change in entropy when the energy of the system is constant and there is no work done in that system. For that kind of situation, we already know that entropy has to be positive for the process to happen spontaneously, and that is what the whole thing about system plus surroundings entropy will increase, or isolated system entropy will increase. So, this is intuitive and this we understand. However, what does this mean? This means that if I talk about an isoentropic situation, for example, an adiabatic process, expansion or contraction, but volume is fixed. So, there is no work done. So, it is neither expansion nor contraction process, and entropy is not changing for the system, the energy is decreasing. What does it mean? So, it means that there is no work done and there is no change in the entropy of the system, that means dq reversible for the system is 0, which essentially means that the change in the internal energy, which is that means the system's energy, let us say the energy of the system was here, it is going below, and this is the amount of energy that is released to the environment, and that release of energy to the environment as a heat increases the entropy of the environment. So, therefore, if you now sum them up, you get 0 from the system entropy, entropy change of the system is 0, entropy change of the surrounding is the change in the delta U of the system divided by the temperature of the surrounding, and that is the amount of entropy that is overall changing, and therefore, overall system plus surroundings entropy is changing by that much amount. So, ds dot in this particular case above is delta U by T of surrounding, and that therefore, is a continuous process, because that is a positive quantity. It is positive because temperature is positive, and delta U is also positive because delta U is negative for the system, that means it is positive for the surrounding, it is going out, and say surrounding is getting the delta U. So, although we might think that system will try to lower down its energy, however, it is nothing but a consequence of the fact that surrounding wants to increase its entropy. Okay. So, that is what we should remember. Now, continuing further, we can see that now let us consider both S and P as constant. So, if we do that, we can write this same equation from equation 7 again, du plus PdV minus TdS less equal to 0. Now, let us take S and P constant. So, what we get? We get du plus PV. So, if I write du plus PV, it essentially means that we have to differentiate both as a du plus PdV plus VdP. Now, if P is constant, then we get du plus PdV. So, du plus PdV I can write as this when my pressure is constant. or this quantity becomes 0. So, I can write that, and so my S and P are constant. So, that will be less than 0. So, therefore, dH at a constant S and P is less equal to 0 for spontaneity, and of course, equal to 0 for equilibrium process. I will just write that in a red color. So, again as you can see that instead of doing the experiment at a constant volume, if I choose to do that at a constant pressure, then I have to consider enthalpy as the determining factor whether the process will be spontaneous or not. In this case also the argument is same, that it is not that the system is trying to lower the entropy, rather it is the entropy of the surrounding that is increasing, because here also the entropy of the system remains 0. So, only thing is that the change in the enthalpy of the system, which of course is caused by both lowering the energy and the work. So, therefore, both of that together it is giving out the effective heat or effective change in the energy of the surrounding, positive change, and that is giving rise to positive change in the entropy of the surrounding. Del H at a constant S and P is less than 0. Let us again write the equation 7, and we write du plus PdV minus TdS less than equal to 0 for from earlier equation. Now, we know that this is nothing but dH minus TdS less equal to 0, and of course, whenever our pressure is constant. So, therefore, we can write that TdS is greater or equal to dHp, and we can write that TdS for both H and P has to be greater or equal to 0. Therefore, for spontaneity T is a fixed quantity. So, therefore, spontaneity ds at a constant H and P has to be greater than 0. I will just write with the red color, ds at a constant H and P has to be greater than 0 for spontaneity. So, you see ds at constant u and v needs to be greater than 0, and ds at constant H and P needs to be greater than 0. Do not mix them together, do not mix H with V or U with P, because then it will not be spontaneous. So, if I say that, can you say that this will be this is a condition of spontaneity or not? It may not, because that will not fit into the thing. So, therefore, remember that these are very important parameters to mention these subscripts. Do not ignore them, do not ignore the subscript, and do not mix the subscripts, because they automatically arrive at when we do this. Okay. Now, coming back again from 7, we write du plus PdV minus TdS less equal to 0. Now, we can take the V as a constant, and we can write TdS less than equal to 0, and we can take the T also as a constant, because why we need to have the T as a constant we will tell you, and we can write U minus Ts when we say both V and T as a constant as less equal to 0. So, let us define a quantity called quantity A as U minus Ts. Now, when you take the derivative dA, you get du minus TdS minus SDT. So, when you take T constant, then you can write dut minus TdS T, and that is what it is here, because we taken T to be constant, and then we took V to be constant to get removal of that term. So, therefore, now we can say that dA for a constant V and T less equal to 0, or for condition of spontaneity dA Vt is less than 0 is the condition for spontaneity. This quantity A, which is U minus Ts, is called Helmholtz free energy. You may not have heard this name till now. You may have heard of a different free energy called Gibbs free energy. We will come to that as well, but this is called free energy for a reason. The definition we are defining as a new thermodynamic potential as U minus Ts, and you will see just like U, just like S, A is also a thermodynamic potential and a state function. It does not depend on path or anything, and you can see that obviously it will not depend on path, because U is a state function, T is a state function, and S is a state function. T is a variable, but it depends on the state only, right. So, therefore, U, T, S all depends on the state only. So, therefore, A also depend on the state, and it is also a state function, and it is then why it is called a free energy, then that is what we need to understand, and that is what we are going to see. So, before we do that, we will just little bit talk about this condition, that why it has to be negative for a spontaneous process. Let us understand a little bit more. So, here we see that A is U minus Ts. So, either for a constant S U need to be less than 0, and that I have discussed that how that means that the entropy of the surrounding will be positive quantity, because U is going there. However, even if S is not 0, then what essentially it means that let us say S is negative quantity little bit, let us say S is negative. So, therefore, if S is negative, then minus Ts will be a positive quantity, and U has to be more negative than the Ts in order for a positive U to go to the surrounding. What I mean by that is that let us say S is less than 0. So, minus Ts is greater than 0. Now, U minus Ts is the net effective energy that is going to go to the environment. So, therefore, if minus Ts is a positive quantity, U has to be more negative than that positive quantity. So, let us say minus Ts is plus 10. So, U has to be 10 or less, let us say minus 11, in order for this quantity to become negative, and if that happens, this minus 1 of energy will go to the environment as plus 1 and will contribute to the entropy of the environment, and that will however, remember, so that has to be, again, that entropy has to be more than the so, and that then only you will get an effective entropy of the system plus surrounding to be higher or greater than 0, and therefore, the process will be spontaneous. So, not only that, and not only like unlike other earlier cases where S was 0, it was just the energy itself was fine, U less than 0 would be a spontaneous process, because S of the system, entropy of the system was 0, but here entropy of the system is non-zero. So, it can be positive, then it will of course boost the surrounding entropy as well, because it will contribute in the overall total entropy as in a positive manner. But if let us say we are talking about del S dot, right. So, del S dot is del S system plus del S surrounding. Now, if this is negative, this quantity has to be positive, more positive than the negative quantity. See, this more positive means that the U, the change in the energy of the system, has to be more negative than the positive part contributed by Ts of the system, if S becomes S is negative. So, that is what it means, that what is the A is giving you that an effective measure, an effective amount of energy that can be used. So, the change in the internal energy of the system U is wasted a little bit in the entropy, you can think of that way. So, you have some 10 rupees you are giving, you have to give out some, in Ts you have to give out some 2 rupees as a tax or something, and then the net 8 rupees that you have is going to be effective. So, that is what the free energy means, that how much available energy is there to be converted to work. So, we can see that by doing a derivation also little bit. So, you know that A is U minus Ts and dA is du minus Tds minus S dt, and Tds is nothing but dq reversible minus s dt, and du minus dq, I will just remind you again, du equal to dq reversible plus dw reversible. So, therefore, du minus dq reversible is nothing but dw reversible. So, this is dw reversible minus s dt. Now, that means at a constant temperature at which actually we define A is nothing but dw reversible. So, this says that, and reversible work, as you know, is work done by the system in a reversible process is maximum. So, if you put a minus 1, that is the work done by the system, that is maximum. So, therefore, the change in the free energy denotes the maximum work that can be extracted out of the system. It is a free energy that is available in order for doing the work, because anything some amount of the work anyway you have to waste in the entropy, which is not going to give you any work. Work is you can say an ordered form of change of energy, whereas entropy is not an ordered form. It says random motions will give you an energy which is not useful. So, dA is a measure of the available maximum work that is possible. Okay, so, now we are going to do the statistical approach a little bit, because we have learned the statistical approach of thermodynamics. So, we are going to now talk about the statistical approach of Helmholtz free energy, and the by definition A is nothing but U minus T s, and U is U, T s, A, they are all macroscopic variables. That means, we are talking about a bulk system, a system of 1 mole of particles and things like that. And we have emphasized that anything that is measurable in a macroscopic sense is nothing but an average quantity. So, this U is nothing but an average energy E, U and E are interchangeably used. So, I am just writing as E minus T s, and what is E? We have defined E, average energy, as E I P I. Well, I is the number of possible states, and S by definition was minus K B P I ln P I. Now, we will just simplify it little bit, E I P I minus minus will become plus K B T P I ln P I. Continuing further, we get A equal to I, take P I common, and we get E I plus K B T ln P I. Okay. So, now we get P I. Now, what is ln P I? We will have to do it little bit on the side to show you. So, P I is e to the power minus E I by K B T by partition function Q, that is the probability P I, right. So, now ln of P I is ln of this quantity e to the power minus E I by K B T minus ln of Q. Now, ln of any exponential quantity is that quantity itself. So, that is nothing but minus E I by K B T minus ln Q. We can write that plus K B T into minus E I by K B T minus ln Q. So, P I E I plus then K B T will cancel. No, it is not yeah, of course, it will cancel and give you E I, and this K B T inside will give you minus K B T ln Q, and this will be minus, this cancels. Now, Q is a constant quantity, K B T is also a constant quantity. So, let us take it outside of the sum. So, K B T ln Q sum over P I, and you know that sum of all probability is nothing but 1. So, we get K B T ln Q. So, therefore, in statistical mechanics, Helmholtz free energy A is written as minus K B T ln q. So, if you know partition function of the system, you are going to know the Helmholtz free energy of the system as well. So, and from Helmholtz free energy of the system, you can also get a lot of other quantities. Now, we are going to consider the another important free energy called Gibbs free energy. So, again we start from equation 7, where it was du plus p dv minus t ds less equal to 0. We start with that, and we are going to take both t and p constant, and what we are going to get is, so du plus p dv is dh minus t ds less equal to 0, or we are going to define some quantity called h minus Ts, and we are going to see what h minus Ts is giving us. dh minus Ts is dh minus Tds minus sdt. So, we have to take, we took t as 0. So, we are going to get dh minus Tds. So, we can write this particular quantity, and remember that in order for du plus p dv to be dh, we needed to take p constant already, otherwise you could not have written that. And once we write that, then basically we are taking both t and p constant less equal to 0, and this h minus Ts is defined as g. So, dg Tp less equal to 0 we are getting for as a condition of spontaneity. So, as a condition of spontaneity, del g at a constant temperature and pressure is less than 0 is the condition for spontaneity, and this is very famous because you might have even studied in your 12th standard that for a spontaneous process free energy has to be negative, and that free energy is basically, they talk about Gibbs free energy. So, this is the definition of Gibbs free energy, which is enthalpy minus Ts Gibbs free energy is extremely important because important for chemical reactions, because temperature and pressures are typically kept constant during a chemical reaction. Pressures are our normal atmosphere pressure and temperatures are our normal atmosphere temperature, which we call as room temperature. Any process that happens where we can see a spontaneous change, for example, if I put water in sodium hydroxide tablets, which we have seen some time back, then spontaneously that gets dissolved and heat gets generated. So, that process of dissolving this one is a free energetically favorable process, which means free energy of the system will go negative. Similarly, if you put sugar in water and sugar will actually dissolve in water, which means the free energy of that system, sugar water system, has to go to negative, change in free energy rather, delta G. So, whatever was there earlier, sugar plus water, and when you mix them together, the free energy of the combined system has to be lower. So, any process, for example, you talk about binding. So, it is very important in medicinal chemistry, where people take drugs, and most of the time those drugs are nothing but molecules that go and bind to proteins, and that binding process overall has to be free energetically favorable process, because if the free energy of the bound complex is negative, then only it will bind, otherwise it will not bind. So, often people calculate or find out new drugs by finding out whether a particular drug molecule will give us a favorable binding to that particular protein or not. Of course, you have to identify which protein is important for a particular disease, protein or DNA, and you have to also find out that the molecule that you are choosing, whether it will have lower negative free energy of binding. If that happens, then of course, we know that the binding will take place favorably. And of course, there is something called competitive binding also is there. If something is already bound, then if you want to replace that, then you have to have something which is stronger than the binding free energy has to be even lower than the previous molecule in order to replace the previous molecule with the new one. So, therefore, the free energy Gibbs free energy plays a very important role. Again, remember, we are talking about only the system. If you think about the overall system plus surrounding, then it is again the entropy, because here also what happens is that effectively is that you are something you are losing as entropy, and then whatever enthalpy you are getting, then that contributes to the surroundings, entropy change and things like that. Essentially it is the same thing. Whenever two things bind together favorably, then the decrease in the free energy will eventually gives rise to positive change in the entropy of the surrounding system. So, system plus surrounding, it is the same always, but always we do not look at system plus surrounding, we only look at the system itself. For example, in protein binding to the drug, we are talking about only protein and drug only, and not something else, not beyond the system of protein, drug and water. Often let us say, see, one of the subjects that I work on is drug DNA intercalation. So, where that there are like flat drugs which go and bind between a pair of base pairs of DNA, and that has to be again a free energetically favorable process, otherwise that process will never happen, and that binding will subsequently stop the DNA replication, and therefore, it is helpful for anti-cancer activity, because in cancer the DNA replication is always goes on, and cancer has several different stages. So, people try to block at many different stages. So, here anti-cancer drugs which are intercalator, that are used in the last stage, where it directly goes to the DNA and stop the DNA replication, and it can stop because it binds. Similarly, for HIV viruses and all, so there are drug molecules that will replace the particular in the binding pocket, that particular molecule that binds, and therefore it inhibits that process. So, free energy delta G is very, very important, and you will see that from free energy delta G you can get lot of other quantities of like for example, change in entropy and enthalpy and many other quantities you can get just from the free energy itself, and we are going to discuss that a little bit now. Which part you are talking about? Okay, 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 very good question. This one, right? Yeah. See, the thing is that U is an average energy, but S is not an average. Okay. So, now the thing is that yes, temperature, if you look at in a microscopic sense, is an average quantity, but we are already taking into account of the averages already, meaning whenever you are talking about e to the power E by kBT, we are talking about the thermodynamic average macroscopic value of the T. We are not really looking at the velocity wise. If we do that, of course, you can still do that, but the equation will be little bit more complicated. So, whenever you write an exponential distribution e to the power EI by kBT, you are already taking into account that okay, system is in thermal equilibrium, every molecule has different velocities, but overall if you measure the temperature, it will give you the T value. So, from Maxwell-Boltzmann distribution, you know that you get only one T value, right. So, that you will get, So, you are using that equation here. Yes, you are approximating that here, but you can, meaning it helps you to simplify the problem. Similarly, for S is again a macroscopic quantity. Here when you are writing it, that you are writing as a macroscopic quantity, you are not writing Kb Pi, okay, you are using PIL and Pi. So, of course, you are using that as a microscopic quantity. So, T you are not doing that to make things simpler and to use it in Boltzmann equation, because otherwise what will happen is that in Boltzmann equation, how will you distribute the energy will become very, very difficult. So, yeah, you are actually essentially taking into account of the average aspect of that already. You are saying that is the reason that you are applying that for equilibrium system alone. Without the equilibrium system, see, microscopically you can have all the information available, but unless it is in equilibrium, you cannot write that T value as one particular value, because every particle otherwise will have different velocities. So, that is why it is very important that these quantities are only applicable for equilibrium and not for, you asked for me that day, na, whether the statistical mechanics can be applied for every, but it cannot be, because Boltzmann distribution is not valid in non-equilibrium situation. G is H minus Ts. So, dG is dH minus TdS minus SdT, and we know that dH is du plus PdV plus VdP, because H is u plus PV. So, dH is du plus PdV plus VdP minus TdS minus SdT. Now we know that from first law, du equal to dq plus dw, or TdS plus dw, or TdS minus PdV. So, du plus PdV is equal to TdS. So, this equal to TdS. So, TdS plus VdP minus TdS minus SdT. So, TdS cancels, giving you VdP minus SdT. So, dg has these two natural variable P and T, as you can see. Similarly, okay, we will do that once more later on. Now, at a constant pressure, dg and temperature, of course, dg Pt is du plus Pdv minus Tds, because that is what we can write as constant temperature and pressure. Otherwise, Vdp term will come, Sdt term will come if they are not constant. So, that is there, and du plus Pdv, you can write that as du plus Pdv minus Tds is dq, we know. So, you can write as dq, and du minus dq plus Pdv, and du minus dq is some kind of W, which is non PV, meaning is some it's a W, that's its W, and Pdv is dW, which is a PV work. So, that means we are getting dW, which is non PV. So, delta G, that means change in the free energy, is non PV work. So, see, du minus dq is just W, some kind of work, all sorts of work, whereas Pdv is work done by volume expansion. So, PV work, wherever there is a work done by volume. Now, when you subtract these two quantities, we are getting work which is only the non PV work. So, therefore, gives free energy is some chemical work which are non PV type. For example, if I bring a charge from far distance to close, so the kind of work that we do, that will be a non PV type of work, and that will change the free energy of the system. So, that is how we can think about the free energy. So, so that means this dgpt is the amount of work required for any external use, exclusive of the expansion or mechanical work. So, dgpt is the amount of work required for any external use exclusive of the expansion or mechanical work. So, we are talking about non-mechanical work as the free energy. Now, we are going to summarize all the thermodynamic potentials that we have learned today. So, we saw that from the fundamental equation that U is a function of S and V, N is also there, but we are not using it, and from there we wrote du equal to TdS minus Pdv. That just came from fundamental equation. Then we have defined H as U plus PV, and we saw that dH is TdS plus VdP. So, here the in case of U, the natural variables are S and V, denoted by ds and dv. In case of H, the natural variables are S and P, denoted by ds and dp. And then we got Tv, V and T for Helmholtz free energy, and we got dA equal to minus S dt minus Pdv. Again, T and V are the natural variables of A, and G we got as a natural variable as T and P, where we wrote dg equal to minus S dt plus Vdp. So, these are 4 different thermodynamic potentials, and they have 4 different variables, and you will see that they are just different forms of each other.